Okay, now, so in the second part of this lesson, we have previously in the first part defined what a unit circle is, and we have discussed the trigonometric ratios on the unit circle, their corresponding axes, in addition to the signs of trigonometric ratios along the four quadrants. So now we're going to move to oriented angles and their principal measure. So we have already discussed the fact that if I had a point P here, then the abscissa of point P would actually be cosine alpha if the corresponding angle is alpha. And over here, the ordinate of P would in fact be sine alpha. However, if I have another point that is moving along the circle over which it completes, for example, several full turns and then stop at point P. The corresponding angle formed with the horizontal axis would actually be alpha plus 2k pi. Remember that 2 pi is equivalent to 360 degrees, so 2k pi in fact represents a certain number of full turns. Well, the full turns could be done either in the positive sense or in the negative sense, depending on k, if k is positive or not, because over here k is an integer. So whenever I am moving on the circle, so I move by an angle of alpha to hit point P, then I would in fact make several number of full turns. Now, having done full turns, I go back to the same point, but the angles are different. The first one has an angle of alpha, and the second one has an angle of alpha plus 2k pi, k depending on the number of full turns I did. If I did 3 full turns, that would be alpha plus 6 pi. However, the angles are different, but having landed on the same point, I would have exactly the same abscissa and exactly the same ordinate. So consequently, this is why cosine of alpha plus 2k pi, if I have a certain number of full turns here, now having this angle inside cosine, so I can in fact remove these full turns and say that cosine alpha plus 2k pi is equal to cosine alpha, because these two angles would have the same abscissa for their corresponding points because they land on the same point on the circle. So I repeat that these two angles, alpha and alpha plus 2k pi, are different. They're not the same angle, but they have the same cosine. If I were to actually show you that on the calculator. Now, my calculator here, I'm not sure if it's set to radian or degree. Let me double check. It's in radian. Okay, so being in radian, in order to make it easier for you to really understand the concept, for now, I'm just going to change it back to degrees. Now, over here, if we're looking for an angle of 30, so if I go for cosine of 30, now this is cosine of 30. According to what we just saw, that if we add the multiples of full turns, which are 360, then cosine would not change. It would have the same cosine. So for example, if I had cosine of, let's just add a full turn, 360 plus 30, now that's a 390. So you notice we have the same cosine, even though 30 degrees is not the same as 390 degrees. And similarly, if I were to add 2 full turns, so 2 full turns would be an equivalence of 2 times 360, so that's 720. So 720 adds 30 to them, so that would be cosine of 750. So you'd notice we have the same cosine. So you'd notice that it doesn't really matter how many full turns we add or subtract to the angle, these two different angles would have the same cosine. And it's similar regarding sine, because when we're adding full terms, we're going back to the same point. Consequently, we have the same abscissa, so same cosine, and same ordinate, so it's the same sine. So in this case, we say that sine and cosine are 2 pi periodic, or they have a period of 2 pi, because the values of sine and cosine repeat every interval of length 2 pi. Okay? However, regarding tan, over here, since cosine and sine have a period of 2 pi, and tan and cotan being sine over cosine and cosine over sine, they would also repeat every 2 pi, but that is not the bigger or the largest period of tan and cotan. In fact, tan and cotan are pi periodic. They repeat every interval of pi. Because if we were to look here at the axis of tan, now this is the axis of tan, and it will be the same for cotan anyway. We're going to see this for tan. So you'd notice that if I had this angle alpha here, now angle alpha would intersect the axis of tan here, leading to this distance being equal to tan alpha. However, as p keeps moving on the circle, when it reaches the point that is diametrically opposite to it, so if you were to in fact reach this point on the circle, which forms an angle of pi plus alpha, or 180 plus alpha, so it's alpha plus 180 degrees, or pi, it's diametrically opposite to it. When you extend that line to intersect the axis of tan, you'd notice that it intersects the axis of tan at exactly the same point. So alpha and pi plus alpha have the same value of tan. Similarly, if we continue, every half a turn, the point would in fact have the same value of tan of its corresponding angle. Every half a turn, whether in the positive sense or in the negative sense, and it's the same thing for cotan. So for that reason, tan of alpha would be the same as tan of alpha plus k pi, where k pi represents the number of half a turn. Okay, now k, if k is positive, the half a turn is done in the positive sense. If k is negative, the half a turn is done in the negative sense. So tan and cotan would in fact be pi periodic. They have a period of pi. And I remind you that alpha and alpha plus k pi are different angles. They're not the same angle, but they have the same value of tan and cotan. Similarly, alpha and alpha plus 2k pi are not the same angle. They're different angles, but they have the same value of cosine and sine. So, however, if we were to define here the principal measure, so everything we've already discussed lead us to something that is called a principal measure of an oriented angle. We have seen that over here, if I have this angle alpha, and if I add infinite number of full turns to it, I always go back to the same point which leads to the same trigonometric ratios. However, so since that oriented angle has infinite number of measures depending on how many full turns I do, only one of them is considered to be the principal measure. The principal measure is the one that is between negative pi and pi. So over here, that interval is in degrees, negative 180, which corresponds to the first two quadrants in the positive sense. If we were to be moving in the positive sense, that's 0 to 180. And if we were to be moving in the negative sense, that would be these two quadrants between 0 and negative 180. So in the negative sense, it would be between 0 and negative 180, while in the positive sense, it would be between 0 and 180. So in fact, the principal measure is a measure that is the measure of the angle that is acute or obtuse, whether in the positive sense or in the negative sense. If In other words, it's as if whatever angle you are given, to find its principal measure, what you need to do is remove the full turns in that angle. So, for example, here, if I'm given this oriented angle of measure pi over 6 plus 2k pi for a given integer k. So for different values of k, you'd notice that theta would actually be one of these angles. This is for k equals to 0, this is for k equals to 1, this is for k equals to 2, etc. This is for k equals to -1, this is for k equals to -2, etc. So you'd notice that among all of these angles, only one of these angles fall in this interval, which is pi over 6. And in fact, since over here the angles are given in radian, a quick way to determine if the angle falls in this interval is to determine if the fraction multiplying pi is smaller or greater than 1. You notice here that the fraction multiplying pi is 1 over 6. So it's smaller than 1. However, for the others, the fraction multiplying pi is greater than 1 because the numerator is greater than the denominator. So only one of these values would actually fall in the interval -pi. So in fact, the principal measure of an angle is unique. There's only one principal measure. It is the angle that is in fact acute or obtuse, whether in the positive sense or in the negative sense. Now, we're going to, in fact, put this into examples here. So how would we, in fact, determine the principal measure if you're given any oriented angle? Now, as I've already mentioned, determining a principal measure is the same as removing the full turns in the angle. So all you need to do is just know if these angles contain full turns, and if yes, just remove these full turns in order to end up with the principal angle. Now we're going to see how we could determine the principal measure of angles given in both radian and in degrees, because the method actually differs a little bit. So over here we're going to start with the angles that are given in radian. So if we were to look at this first angle here, I'm given this angle that is 102 pi over 7. Now this angle is clearly greater than pi, so this angle does not fall in the interval -pi. And I think I forgot to actually mention something on the previous slide, is that you'd notice that the interval is opened on -pi and the interval is closed on pi. So pi is in the interval, -pi is not in the interval. It's for a reason that if you look on the trigonometric circle, if you go from 0 by 180 degrees or by pi radians, you'd fall on this point of the circle. If you'd go in the negative sense, that would be the point corresponding to -pi as well. So pi and -pi correspond to the same point on the unit circle. So consequently, one of them has to be the principal measure of the other one. So that is why it is considered by convention that pi, the positive angle, is the principal measure of -pi. Okay, so let's go back here. So we agreed that theta does not fall in the interval -pi because the fraction multiplying pi is greater than 1. So I'd need to determine how many full turns there are in 102 pi over 7. So in fact, what you need to do here, this is 102 pi over 7. So I need to determine the multiples of 7, the denominator, the multiples of 7 exactly around 102. So I think there are 105. I think 105 is divisible by 7. Yes, that's a 15. And 7 times 14 would actually be 98. So that's 98 pi over 7 and 105 pi over 7. If you're not sure how to define the multiples of pi, the multiples of 7 around 102, all you have to do is just divide 102 by 7. It gives you 14.5. So they're 14. So the numerators here would actually be 14 times 7 and 15 times 7. Okay, so over here, this is 14 pi. And over here, this would be 15 pi. Notice that these two should end up giving you consecutive integers or multiples of pi, or else something is wrong. For example, if you had a 13 and a 15, it means that you have missed one. They have to be consecutive, like 14 and 15. Now, which one should we basically consider in order to remove the number of full turns? Remember that a full turn corresponds to 360 degrees, or 2 pi in radian. We're working in radian here. So it corresponds to 2 pi. So I need to eventually consider the one that is even. So 14 pi is an even multiple of pi, while 15 pi is an odd multiple of pi. So 15 pi's are not full turns. However, 14 pi's are full turns, and they correspond to 7 full turns. So over here, in order to determine the principal measure of theta, so the principal measure of theta, if I were to call it alpha, you cannot call it theta because it's not the same angle. Okay, they're different, but alpha would be the principal measure of theta. So what you would do is, in fact, consider theta minus the number of full turns that you have found. So it's 102 pi over 7 minus 14 pi, and 14 pi is 98 pi over 7, having the same denominator out of 7 would lead you to 4 pi over 7 rad. So the principal measure of this given angle theta would in fact be 4 pi over 7, and you can clearly see that the fraction multiplying pi is smaller than 1. Okay? So if we were to do the same thing for the other angle, but watch out here that this other angle is negative. So for example, a negative 84 comes after negative 85, because here a negative 84 is greater than negative 85. The numbers are negative here. So similarly, I need to look for multiples of 6 around negative 85. So what you would do is divide 85 by 6. It also gives you a 14. So a 14 times 6 is an 84. So over here, so it's a negative 84 pi over 6, which is negative 14 pi. And the one that is smaller than negative 85, just add 6 to 84, that's a 90. So that's a negative 90 pi over 6, which would actually be negative 15 pi. Again, this is odd, an odd multiple of pi, so it does not represent a number of full turns. However, it's the even multiple of pi that represents a number of full turns. So if I were to consider the principal measure alpha, corresponding to that angle theta, so the principal measure would actually be theta, which is negative 85 pi over 6, minus the number of full turns we have found, and don't forget here that this is negative, so it becomes a plus 14 pi, so which leaves me with negative pi over 6. So the principal measure of negative 85 pi over 6 is negative pi over 6 radian. So this is how you would determine the principal measure, is by removing the full turns existing in the angle. Now this is when the angle is given in radian. Let's just over here go through these in order to determine how to determine the principal measure if the angle is given in degrees. Now similarly to what we've already done, we need to remove the number of full turns. Over here, when the angle is in radian, full turns in fact correspond to 360 degrees. So in order to know how many full turns the angle has, you'd have to actually figure out how many 360 degrees each of these angles have. So over here, theta would in fact be, in order to determine how many 360 degrees we have in 1220, all you have to do is just divide by 360. So it's 3 point something. So the full or the whole part is 3. So there are 3 full turns. So it's 3 times 360, and I need to actually determine the remainder of the division. So in order to do that, I do 1220 minus 3 times 360, which is 140. So usually when you do that division, you could end up with the remainder in the interval negative 180, 180, so it would be the principal measure. However, sometimes in some cases, the remainder is outside the interval negative 180 and 180. We'll see then what we would do then. Okay, so over here, the principal measure is in fact alpha equals to 140, because over here, the remainder does belong to the interval 180, negative 180, 180. So 140 is the principal measure. We have removed the full turns, and that is the principal measure of the angle. If we were to do the same thing here, theta is 2,350. So 2,350 divided by 360 gives you 6 full turns. So it's 6 times 360, and I need to actually determine the remainder. So it's 235 minus 6 times 360, which gives you 190 for the remainder. Note that since here you're dividing by 360, so you could have a remainder that goes strictly up to 360. So because the remainder should be strictly smaller than the divisor, and the divisor here is 360, so there is possible to determine to obtain a remainder outside this interval. So it's not in negative 180, 180. So not being in this interval, it means that this remainder still has a full turn. So for the principal measure, all you have to do, since it's positive, if the remainder is positive, in that case you'd subtract a full turn from it. If the remainder is negative, you'd add a full turn. So 190 minus 360, which would in fact gives you negative 150 degrees. So negative 150 degrees is the principal measure corresponding to theta. So if we were to move to the last example where we're given theta as a negative angle. So usually when you do that, please do not perform these operations on the negative angle. Just multiply by the negative at the end. So at first, just start with the positive angle. Divide by 360, it's 1785. Divide it by 360, it gives you 4 full turns. So 4 times 360 plus, I determine the remainder. So it's 1785 minus 4 times 360, which is 340. Is it a 5? Yes, it's a 5. So 345. Now theta is a minus multiplying that, so it's negative 4 times 360 minus 345. 345. So you'd notice that this angle is not in the interval negative 180, 180. When it is in the interval, you just take it as a principal measure. When it's not in the interval, in this interval, you'd actually add or remove a full turn. It means that that remainder still has a full turn in it. So over here, the remainder was positive, so I subtracted a full turn. Here the remainder is negative, so what I would do is add a full turn. It's always the opposite operation, because negative, if I subtract 360, you would still be going further than that interval. So over here for the principal measure, what you'd actually do is negative 345 plus 360. So alpha would in fact be 15 degrees. So the principal measure here is 15. Just keep in mind that this is the interval corresponding to principal measures. Okay, for example, here I had a 190. So what I did is subtract 360 in order to bring it back to the interval. Well, this one was a negative 345. So what I did is add 360 in order to bring it back into the interval. So this is why you'd go by the opposite operation, because over here if you subtract 360, you'd be going further than the interval, so you would not be going back to the interval.